Okay, so our topic for this week is energy use in agriculture. And it, of course, takes energy to make the things that we eat. There are going to be several classes of energy that we consider here. First of all, there's what we call direct energy, and that's the energy from natural gas and from electricity that they use to power their barns and their tractors, etc., etc. So that's direct energy. But there's others. There's the embedded energy, or you could also call it the indirect energy, and that's the energy that was used to make all their equipment, all their buildings, the seeds that they use, and in particular, the fertilizer they use, which is a tremendously energy intensive process. So that's indirect. So we've got the direct, we've got the indirect, and then of course, we also have transportation energy and processing energy. So when we say embedded here, it's especially important with agriculture that we realize that that's not the food energy. That's the energy it took to make it. Really, the food energy is embedded in the product. There's food calories in there, and you can recover those. You can metabolize that food and unleash that energy. So, the food energy really is embedded. The embedded or indirect energy isn't embedded in the product, but it is embedded in terms of that was the energy that was required to make the food product. So here's an example. These are some numbers from the U.S. Department of Agriculture for the amount of energy to make an apple. So we've got some direct energy. So here, let's just try and draw a picture here. Okay, so here's a tractor. Okay, that's the direct energy. So what did we say? Okay, that's about 69.5 kilojoules. 69.5 kilojoules. This is a single apple, okay? 69.5 kilojoules to run the tractors and use all the electricity use. And then the indirect stuff, okay? So what graphic will we use for that? Okay, well, that'll be like the seeds and the fertilizer. That looks like water, but anyway. Here, let's label these. These are the seeds. And the energy to make their buildings, that's another 69.5 kilojoules. Surprisingly large, okay? Then, of course, once you have farmed your apples, you've got to ship them. There's a picture of an apple. And so let's put it on a truck. There's a big truck. Okay. And then we transport that. And I estimate with about 500 kilometers of trucking, then that is going to be about 160 kilojoules to transport that apple to us, and relatively large compared with the direct and indirect. And then inside the store and inside our homes, we've got to put it in the refrigerator. So here's the apple on the inside here, inside the fridge. And if you had, say, 400 apples in a refrigerator at a processor for 6 days, that's about 259 kilojoules. So if you add all of that up, you get a total of about 500 kilojoules. And then, of course, the apple itself, the food energy that's in it, typically, that would be about 95 calories. That's about 400 kilojoules. And here we have the problem of sustainability, at least in terms of how food is, in terms of how it applies to food. You see that we're actually putting more energy in than we're getting out. Historically, this wasn't the case because agriculture, you put in a little bit of energy and you got out a lot of food, and that's what enabled us to grow. Because we didn't have fossil fuels at the beginning. The energy we were using was all human labor. So we had to be getting more food energy out than the human labor energy we were putting in, or we would have starved. All right. So there are some extremely poorly drawn graphics. I imagine many of you can do better. Let's try a second example. Let us consider tomatoes that could come from California and tomatoes from the BC hothouse, and just see which is better energy-wise. So here's our model. California, of course, we expect lots of transportation energy. There's lots of sun and high temperatures, so I'd estimate we could use less fertilizer. Here's the value for the embedded energy of nitrogen fertilizer, quite high. In our model, this is a number I got out of a paper somewhere. It was 2 megajoules per kilogram of harvest, and that was the energy, the direct energy to run the tractors and buildings. Here's the indirect energy for all the buildings and tractors. Here is a direct energy term to pump the water. In California, most of the water actually gets pumped up from rivers and lakes up over the set of mountains into the Central Valley. So there's a tremendous amount of energy required to pump the water up the hill. And then there's pumps along the way to distribute it to the field. So there's quite a significant amount of energy that's used to pump water in California. Here's a typical yield for a fruit product like tomatoes, but my friends in horticulture tell me that tomatoes are actually berries and not fruit. Okay, so the hothouse, here's our model. It's close by, only 20 kilometers. Hothouses use considerable amounts of natural gas per heating. And then there's lots of electricity because they have lights and pumps and fans to circulate the water. Probably a little bit more fertilizer because we're further north, so there's less sun, less heat. To get a reasonable yield, you've got to fertilize the soil. Of course, with the greenhouse, you expect there's a lot of energy locked up in the glass and steel, and that turns out to be the case. You get lots of yield out of a greenhouse on an annual basis just because you get lots of crops. So yields are typically expressed in tons per hectare. A hectare is about 10,000 square meters. In both cases, California and hothouse, we've got some energy locked up in the seedlings, and then the product of those tomatoes needs to be refrigerated, packaged, put out in the store, all of those things, moved around from the truck into the warehouse, etc., warehousing energy, and a value from the USDA is 3.3 megajoules per kilogram. So let us now work out the total energy signature of these tomatoes, one from California and one from the hothouse. All right, so starting with California, the direct energy, there's two things to consider. First of all, there's the energy to run the equipment, and that was 2 megajoules for every kilogram of berries, tomatoes. Then we had the energy to pump the water. Now that was given as 9 gigajoules for every hectare in production. Now first we've got to convert gigajoules to megajoules. There's a factor of 1,000 there. And next we want to convert hectares ultimately to kilograms. We do that using the yield. A hectare of field gave us 15 tons of product, and a ton is of course 1,000 kilograms. So if we check our units, gigajoules will cancel, hectares will cancel, tons are cancelled, and now we know how many joules were needed per kilogram of product. If you work that out, you find the direct energy signature of the California tomato was 2.6 megajoules per kilogram. So that's energy the farmer would have to pay for directly to his utilities. Of course, there's lots of energy that he pays for indirectly in his fertilizer, the seeds, the buildings, and the equipment. Okay, so for the fertilizer, we said about 300 kilograms of nitrogen fertilizer for every hectare in production. Now, that fertilizer, it takes about 40 megajoules to produce a kilogram of it. That's per kilogram of fertilizer, not per kilogram of product. So now we've got the megajoules of energy per hectare, and we want to convert that to megajoules again per kilogram. So we will use the same two ratios here. Here's the yield. A hectare gives us 15 tons, and of course a ton is 1,000 kilograms. So that will give us the energy embedded in the fertilizer. And that works out to be, if you work out the numbers, 0.8 megajoules per kilogram. Now the seeds were given as 0.5 megajoules per kilogram. And then the farm equipment, which lasts for quite a long time. So on an annual basis, there's not really that much. So if you add this all up, the 0.8 here for the fertilizer, the 0.5 and the 0.2, you end up with an indirect energy contribution of 1.5 megajoules per every kilogram of tomatoes. Next, transportation. We expect this is going to be large, and indeed, for California tomatoes, it doesn't disappoint. There's 3.2 million joules to transport a ton a kilometer. We want this in megajoules per kilogram, not megajoules per ton. So a ton is 1,000 kilometers. And now the tons cancel out. So 2,500 over here times 3.2 divided by 1,000. So there, as we might expect, every kilogram of tomatoes took about 8 million joules to get it to us. Processing, this was just a given number, surprisingly constant over a wide range of food products. So now the total embedded energy per kilogram for our California tomato was 2.6 plus 1.5 plus 8.0 plus 3.3, and all of that is megajoule per kilogram units. Okay, so that works out then to, how much was that? 15.4 megajoules per kilogram of tomatoes. Now, since the tomato itself is only about 0.7 megajoules per kilogram, you can see that we're not really getting a great return on our energy investment. For 15 megajoules per kilogram, we're making only 0.7 megajoules per kilogram of tomato. But of course, tomatoes aren't very energy intensive. It's more for the minerals and all of those other wonderful nutrients. So it's not necessarily a bad investment of energy to get all that healthy stuff. Okay, now let's consider the hothouse. Well, we have to heat the building, and that took 30 gigajoules for every hectare of building. Now, of course, we want to express this in megajoules per kilogram, so we convert gigajoules to megajoules, and then we use our yield to convert from hectares to kilograms. So a hectare gives us about 60 tons in the greenhouse, and a ton is 1,000 kilograms. So that number there, that works out to 0.5. So about 0.5 megajoules for every kilogram. And then we were told about 5,000 kilowatt hours for every hectare of greenhouse. So that's 5,000 kilowatt hours for every hectare of greenhouse. There's 3.6 megajoules. My handwriting is just terrible here. Let's try that again. 3.6 megajoules for every kilowatt hour. And then once again, we convert per hectare to per kilogram. And the 60 and the 1,000 is just 60,000. 60 tons is 60,000 kilograms. So that gives 0.3, I believe, megajoules per kilogram, for a total of 0.8 megajoules per kilogram, which was a lot less than the California tomatoes, simply because, well, you don't use a lot of energy to drive tractors around in a greenhouse, and you, in BC anyway, don't need to use very much energy to irrigate, because we have lots of rainwater and it's captured in the mountains nearby, and we don't need to pump it. It just runs downhill to the greenhouse. Of course, the greenhouse is going to fall behind when it comes to considering the indirect energy, because the building itself, of course, is going to consume a tremendous amount of energy. Just give myself a bit more space here for that purpose. All right, so the fertilizer, well, we're using a little less, or sorry, a little more because we're more northerly, 500 kilograms per hectare. It still takes about 40 megajoules to make a kilogram of fertilizer, not a kilogram of product. And then we again just convert that to the yield. A hectare makes 60,000 kilograms. So that works out to 0.33 megajoules per kilogram. Then we've got the seeds. And as before, we said that was about half a megajoule to make a kilogram of seeds. And then, oh, we've got the building. And this is going to be quite a calculation here. Because for the building, we've got to add up all the components. So we have 250 kilograms of glass. And it takes 16 megajoules to make a kilogram of glass. Then we've got 200 kilograms of steel, and it takes about 30 megajoules to make a kilogram of steel. Then there was about 10 kilograms of plastic fittings, and it takes 100 megajoules to make a kilogram of plastic. Now that's the energy per building. That's the megajoules to make 10 square meters of building. Per hectare, of course, there's 10,000 square meters. So this now, we've scaled it up, is the energy to make a hectare of building. Okay, that'll be the energy per hectare. But of course, the building lasts 20 years, and all of these other values here are annual values. So we still need to divide by 20 years. And then we still need to find a little room here on the end to convert this to per kilogram. And we do that by saying the hectare produces 60,000 kilograms. So that sits over here on the end. Okay, so there's the energy to make 10 square meters. You multiply by 10,000 over 10 to find the energy to make a hectare. You divide by 20 to make it an annual value, and then you convert per hectare to per kilogram. So this building term ends up being quite large. It's 9.5 megajoules per kilogram per year, and that's understood. So here we have then the total indirect energy for the hothouse, and we see it's 10.3 megajoules per kilogram. That's the total indirect. So tremendous amount of energy just locked up in making that greenhouse. Now, this is quite local, so we're not expecting a whole lot of transportation energy here. It's only 50 kilometers. So 3.2 megajoules to transport a ton by a kilometer. And a ton, of course, is 1,000 kilograms. So tons cancel, kilometers cancel. This works out to be 0.64 megajoules per kilogram. And then the processing as before was 3.3. So if we add this all up then, the indirect was 10.3, the transport's 0.64, the processing is 3.3, and the direct is 0.8. So surprisingly, we get something that's fairly close to the California value. Almost exactly the same number. Oh, this is a little bit better, I guess, right? Because that was 15.4. So this is a tiny bit less for the locally grown hothouse tomato. And so here's a summary graphic. So yeah, they're almost the same. This bar is a little bit too big, I think. But there you have it. So the Californias are a lot more direct energy because of driving the tractors and pumping the water. The BC hothouse uses a lot more indirect because you have to build the greenhouse. The California uses a lot more transportation because it's further. Processing's the same. They're basically about the same in terms of the total amount of energy that it takes to make it. So we were getting about 15 megajoules per kilogram to deliver, what was it? It was 0.7, I think. Yes, 0.7 megajoules per kilogram of tomatoes. And to the tomato people out there, all I'll say is that I hope you've really enjoyed listening to me use the word tomato for the last 15 minutes. I have to hear you saying tomato all the time. I'm sure it's been very irritating for you, but what goes around comes around. I'm going to go eat some tomatoes now and put some tomato ketchup on my fries and have some tomato soup, have a nice tomato salad, and yeah, so that's it. All about tomatoes. Have a good one.